All right, everybody, welcome to Your Science. Let's talk the absorption and radiation lab. So you should only be doing this if you've done all three sections already with the lamp and the two objects that you heat and cool, right? Let's have our definitions be really just that simple. There's no reason to get fancy with these. Absorption will be when the object heats up, so it's taking in energy. Radiation is going to be when the object cools down because it's releasing its energy. And hidden within that, that's really the key to what we got to see here. That when things cool down, it's an energy transfer out. Energy doesn't get destroyed in this process. So, like if I were to replace the different objects that you did in this lab with this dinosaur here that looks scared to be sitting in front of this lamp, yes, and try to draw this as close as you can to what I'm drawing here. So if you turn the lamp on, yes, it heats up. And there's a wavelength of energy that would come out of that lamp and hit that dinosaur. And it would make it warmer. Now, anything that's warm is giving off energy at the same time. It's radiating its energy back out. But there's like a running balance, right? If more energy is coming in from that lamp than is going out from radiation, then the net result is that that dinosaur gets warmer and warmer. When we turn off the lamp and remove it, then more energy is radiating off of it than is coming in, and the net result is that the dinosaur gets cooler. There's a huge difference, though, in the wavelengths of the energy that come from the heat source, from the lamp, which is really supposed to be the sun, right? This lab's all about the sun heating the Earth as it rotates towards the sun, which we call daytime, the Earth gets warmer, and then spinning away from the Earth, which we call nighttime, the Earth gets cooler. When something radiates its energy off away, it does it at a much longer wavelength. So I'm being very deliberate with how I draw these little curvy lines. A wavelength, the definition of wavelengths is from one peak to the next peak. How long is that? These that are coming off the dinosaur are much longer, right? So let's chuck some words over here to indicate some of this. Energy from the sun is at a shorter wavelength. And energy from objects is at a longer wavelength. Jeez. All right. And that, again, if there's more of that going on, the net result will be that this thing is cooling. This longer wavelength energy we're going to need to know is called infrared. INFRARED. Everything that's warm gives off infrared energy. The warmer it is, the more of it it's going to give off. And then again, if you can keep that in mind as that's what is going to cool things, you're starting to get there. So like I'm giving off infrared energy right now. Now my body, I'm alive. I'm turning cookies into energy. I'm metabolizing my breakfast and staying warm. Like that's how humans work. But if it's just an inert object, like this piece of plastic, it's got a certain temperature. It's giving off some infrared energy right now, which would be cooling it off if it weren't being kept warm by other things. Now, the trick to all of that is that infrared energy gets trapped by the atmosphere. So I don't know. Sometimes I draw little like asterisks here to say that this isn't going to make it back out into space. The way that energy from the sun comes right through the atmosphere, hits the surface of the Earth. If it were to just bounce, like hit a snow-covered field that's white, it's just going to go bouncing right back out into space, right through the atmosphere as easily as it came in. If it hits something and that thing warms up, though, that thing then gives off infrared energy, and the atmosphere is good at holding on to that infrared energy. Infrared. This is known as the greenhouse effect. Now, you have noticed this. There's no way you haven't noticed this, because if you have a car sitting in a parking lot in the sun, you've had this happen. You go inside, the sun, again, at the shorter wavelength, if you could try to draw this as accurately as you can with me, that'd be great. The shorter wavelength Goes right through the windows, no problem. Passes right through them. And again, if it hits something shiny, like the chrome of a seatbelt, or people put those shiny reflective things in the windshield. If it hits stuff like that, it bounces right back out at the same wavelength. There's no energy transfer, so it passes right back through the window again. Where this is a different process, and where even though it feels very obvious, I want to take my time and make sure that we understand it, is that if this seat gets warm, then it gives off infrared energy, which is a longer wavelength, which does not make it back out through the glass. It gets trapped by the glass. So the net result is the air inside the car gets warmer and warmer and warmer and warmer. That's the greenhouse effect. It also happens in greenhouses, after all, right? That's why we have them. Sun can get into the greenhouses. The things inside them get warm. Those warm things then give off energy that gets trapped by the plastic or glass or whatever kind of greenhouse it is. Okay, that's the basic physics, undeniable physics of the greenhouse effect. Now, you may have heard this stated in a negative tone before, or say like maybe it rings a bell with climate change and with global warming, and you might say, "Oh, that's bad." The greenhouse effect is not bad. We love the greenhouse effect. Think about what would happen if there was no greenhouse effect. If when the Earth cooled, if all that energy just escaped off into space, what would happen when we spun towards the sun? Daytime, we got warm. When we spun away from the sun, nighttime, if all that energy just left, it'd be freezing. In fact, this happens on the moon. And I forget the exact temperatures, but somewhere down around negative 260 at night, pretty darn cold, up to somewhere around 260 to 270 during the day. Let's just say 260 again. Plus or minus 10, 15 degrees on either one of these. But even if I'm off by that much, that's a giant swing. That's like a 500-degree swing between night and day. People complain here when it goes down by 10 degrees overnight. 500 degrees, we wouldn't have ever evolved. Life as we know it would not exist. So this greenhouse effect, think of it like a blanket. When the Earth spins away, that layer of atmosphere that we have on it traps the infrared radiation coming off the planet and keeps that side of the planet a little bit warmer, which is wonderful, right? But life as we know it evolved with a certain amount of greenhouse gases in the atmosphere. The stable conditions that was required for life to be as successful as it is relied on a relatively stable atmosphere. Yes, things change through geologic time, oftentimes with disastrous consequences for life, but those changes also are pretty slow. So having those changes happen quickly because of what the humans have done to this planet, that's where it might get a little scary. There's a runaway greenhouse effect as an example of what can happen if this really gets out of hand. Now, humans didn't do this on Venus. It's just because of the nature of the planetary geology of that planet, the Venus science instead of the Earth science. There's a lot of carbon dioxide in the atmosphere there. It's a very efficient atmosphere at holding on to radiated energy. And the temperature on the surface is almost 900 degrees Fahrenheit. It's hotter than Mercury, which is closer to the sun. Hot enough to melt lead on the surface of the planet. And again, the greenhouse effect is what we have to think about that. Thank for that. So again, if we humans want a stable environment in order to have life remain on the same track that it has, we've got to be careful about the amount of greenhouse gases that we're emitting. Carbon dioxide, the big one. Methane is a big one, which is CH4. I say amongst others, occasionally the regents which loves to ask about these two, occasionally the regents will also say water, H2O. And yes, that water is a greenhouse gas. Not one I tend to like. These two we're manipulating. The amount of water that's in the atmosphere is kind of going to be set by the environment already. There's not going to be a lot we can do to increase or decrease the amount of water in the atmosphere. There's a lot we are actively doing to increase the amount of these two in the atmosphere. Yes, all three behave as greenhouse gases, but these are the two culprits that we really got to pay attention to. With the lesson being, and we'll build on this the rest of the year, as we try to understand how to emit and control and maybe even sequester, take some of this out of the atmosphere, because greenhouse gases are good absorbers of infrared radiation, trapping that heat, holding onto it. And the more of that we have, the warmer the planet will be, just as a matter of the simple physics of how energy transfers. Okay? All right. Let's keep on going. No, let's keep on going. So what we should see with our data, whether your lab worked perfectly or not, maybe it did, maybe it didn't. Our equipment is so-so, right? And maybe our methods were off a little bit, and things happen during labs, right? But out of the three of them, I bet you got one to work. And one important earth science rule that pops up a lot is that a good absorber is also a good radiator. Maybe a better way to say that is that things, well, let's type it with that. Things that heat quickly, cool quickly. And the opposite, if it's not obvious, that's things that heat slowly, cool slowly. That's big. You've noticed this before. I'll show you where. Let's talk about what happened in this lab. The covered, trying to imitate the greenhouse effect, should cool slower than uncovered. And again, we'll just make a little note on here because when we get to your conclusion, you might just want to refer back to it. This is to mimic the greenhouse effect. Maybe yours worked, maybe it didn't. We'll see. Black should heat and cool faster than shiny. If you've ever worn a black shirt out on a sunny day in the summer, you've probably recognized that. Sand should heat and cool faster than water. Here's where maybe you've noticed this before. If you've been to the beach, you're on the beach in bare feet in the sun, it's hot. So what do you usually do? Yes, you can put on shoes, but you also sometimes go running into the water, right here in Lake Ontario, and it's cool. There's this experiment in real life. It's the same sun beating down on the same area. It hits the sand, it hits the water, but the sand heats up a lot more, a lot faster. It would be very bizarre if when you ran to the water, it was as hot as the sand, right? Beaches people wouldn't go to them. It'd be miserable if the water was that hot, right? So you've noticed this. You've kind of proven this. You've done an earth science experiment on your own in the past. That sand heats and cools faster. Go back at night and the sand's going to drop way down that quickly. Look outside, unless you're looking at this in another time, but look outside right now. We just had our first big snowstorm, if you need a time flash, late November. In the last week, 2 weeks, the ground has gone from not frozen to frozen like that very quickly. Lake Ontario, sitting right next to this ground, is not frozen because things that heat very slowly, the way that water does, like it doesn't get that hot at the beach, also cool very slowly. Lake Ontario is like a big heat battery. It's 800 feet deep at the deepest point. It's a ridiculous amount of water. So it takes all summer getting very, very slowly warmed up, and then all winter very slowly cooling off. Never really freezing over. Yes, some pack ice can blow down here, but it doesn't freeze the way that smaller lakes and ponds do because water holds onto its heat energy so well. It's why you use it in radiators. If you heat with a radiator, there's something in your basement to heat water, then that water goes through the house and slowly radiates its heat out into the radiators, into the rooms, right? If water cooled quickly, you'd heat it in the boiler in your basement, it'd travel across the basement and lose its heat like that. And then that wouldn't be a very good heater, would it? So all of that comes down to this property. You may have never heard this term before, specific heats. This is a list of specific heats. This can be found on the front page of the ESRT, Earth Science Reference Tables. A bunch of common materials and their specific heats. So what is specific heat? Take this unit right here and break it down, and we'll define it by just seeing what this unit says. It says how many joules, which is a term, it's a unit of energy. And again, one maybe you haven't heard of, but how many joules? So how much energy does it take to heat a gram of something? That's why there's a gram right here. 1 gram of a substance by 1 degree Celsius. So this is a crazy looking unit, but it really tells us exactly what it does. 1 degree C. How much heat energy does it take to heat a gram of a substance by a degree Celsius. Basalt, it's a kind of rock we'll look at eventually. Takes 0.84 joules to take 1 gram of basalt and make it go up by 1 degree due to the physical nature of that property, of that substance, the physical properties of that substance. Copper takes 0.38 joules of energy to get 1 gram of it to go up by 1 degree C. But look at water. Water takes 4.18. Water has a very high specific heat. It takes a lot of energy to get it to warm up. But then conversely, since it takes so much energy to get it to warm up and it warms up very, 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 very slowly, it also cools off very, 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 very slowly. So what does this mean about the energy that it takes to heat up water? It takes a lot. Means that it heats and cools very slowly. And now that may seem weird, like you boil water all the time. You do it for coffee. You do it for macaroni and cheese, right? But it does. It takes a lot of energy. If you put an equal amount of copper in an equal amount of water, the copper is going to heat up more in that heat energy than the liquid water is, which again is why Lake Ontario acts like a heat battery. It very slowly warms up, holds onto that heat really well. I lived in the Midwest in Minneapolis, where there's not a Great Lake right next to us, and it's only a little tiny bit further north. It's very similar latitude, so very similar sun. And it's ridiculously cold there in the winter, all winter long. You don't get the warm days. There'd be wind chills in the negative 30s, 40s. We still had school. It was a very, very, very cold place to live. And I blame that. I don't blame it. I account for that with this idea that liquid water has a very high specific heat. All right. Finally, down to business. You got 3 sections here: sand versus water, black can versus shiny can, and covered versus uncovered. So I know this is a major lab. This is like our big project, our biggest lab of the year. Chuck all your numbers for sand and water. Down here, the axes on the bottom is for time. Minutes. There's 30 boxes here for 30 minutes deliberately, so you're going to want to label those like 0. I mean, you can label every single one if you want. 2, 3, 4. But you'll probably drive yourself a little crazy, so sometimes I do it like every 5, 6, 7, 8, 9, 10. And so on. Do that right to the end. That's the same on all 3. Your y-axis, you can come to me for help. I've got a little spreadsheet. I help people figure this out. I do it if you're in class. I've been doing it for people the whole time. You don't want to like start at 0 and go to a high number if that's going to make all your data basically look like this. You know, if it only went up by a couple of degrees and down by a couple of degrees, let's start at a number down here that's appropriate and end at a number up here that's appropriate, so that we end up using more of the scale. You got to have each box be worth an equivalent amount as you do that. It's not easy. And if you need help, just say, hey, Finn, can you help me out with the graph on page whatever? And I'll open yours up in Cami and I'll chuck it right on there for you. At least get you started, then you can do it. Then you chuck all your dots. Ideally, I won't do the dots. Ideally, like you'll have one that heats and cools faster. This would be like perfect data. And then one that heats and cools slower. Now, given the state of our equipment and our methods, maybe it doesn't look perfect like that. But give me what you got. Don't try to like falsify the numbers that you ended up with. These 4 questions were on the overhead at the end of each experiment, so you may have already done those in your lab books, and then do it again, and then do it again, and then we'll talk rate of change problems after that. All right, thanks for tuning in, everybody. I know it's a long one. Good luck.